We were talking yesterday then about trapezoidal rule, right? All we had to do was add up all these trapezoids. And we said that the area of each trapezoid is just equal to 1/2 times B1 plus B2 times H. But these trapezoids are turned sideways, right? So the height is really just delta x. Agreed? And the bases are just the values of the function at the left and the right. Okay? So then let's take another look at this. So if we were to let's redraw this. So here's our function, and we're going to go from A up to B. Well, this is just the same as x sub 0. That's x sub 1, that's x sub 2, x sub 3, etc., right? And so these just define the trapezoids, right? All the way over to x sub n. Okay, well let's look at these. Let's just look at these and add up the areas. So this first one, let's make the first one red. Just looks like that, right? So the area of the first one, we'll call that A sub 1, is just going to equal 1/2 times f of x sub 0, right, plus f of x sub 1 times delta x, right? Everybody agree? Okay. What's the second one going to look like? The second one will make blue. It is. It is, right? So it's going to equal 1/2 times f of x sub 1 plus f of x sub 2 times delta x, right? Okay, we'll just do a few of these, but you're going to see something happening here. Third one's going to be purple. Okay, so A sub 3 is 1/2 times f of x sub 2 plus f of x sub 3 times delta x, right? Let's go all the way up. Let's just do two more. So this is x sub n minus 1. That's x sub n minus 2, right? So let's do this guy. So A sub n minus 1, right? Everybody agree? Is equal to 1/2 times f of x sub n minus 2, right, plus f of x sub n minus 1 times delta x, right? And then last one, would be A sub n equals 1/2 f of x sub n minus 1 plus f of x sub n times delta x, right? And we're just going to sum all those up to get the total area. Agreed? So we're just going to take that sum. Is there, if I think about that sum being written all out, is there anything we could factor out of each term? 1/2 delta x, right? So then we're going to get, if we do this, okay, we're going to get A equals 1/2 delta x times just a bunch of stuff, right? So this first one was just going to be f of x sub 0 plus f of x sub 1. Second one was f of x sub 1 plus f of x sub 2. Third one was f of x sub 2 plus f of x sub 3. Second to the last one was f of x sub n minus 2 plus f of x sub n minus 1. And then the last one was f of x sub n minus 1 plus f of x sub n. What pattern do you see there?
Besides the first and the second term, I mean, first and the last term, you repeat everything twice.
Everybody see that? Every single one of those values is double counted except the first and the last, right? So our trapezoidal rule really then just looks like this. The area by the trapezoidal rule just equals delta x. And what is delta x again? B minus a over n, right? So we're going to get b minus a over 2n, because we're multiplying by 1/2, right? 1/2 delta x. Everybody agree that's it? Times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub n minus 1 plus f of x sub n, right? That's one way to write the trapezoidal. Okay, I like to write it a little differently. I like to write it as, I like to partition this part off as an interior sum, right? So if you do that, you could write it as it's equal to b minus a over 2n times f of a, right? Plus, how would I say that? That's 2 times the sum, that's terrible sum sign, I gotta do better than that. Plus the sum of f of x sub I as I goes from 1 to n minus 1, right? Everybody agree? So that's just going to be x sub I is just f of a plus I delta x as I goes from 1 to n minus 1 plus f of b. And usually I just collect those together at the beginning and then do the interior sum, right? That's not the way the book writes it, but to me, that's a much better way to do it. Okay? So let's try this. That's it. It's really simple. If you want to make an estimate using the trapezoidal rule, you just do that, right? So let's try like a sample problem. How about if we want to estimate, for example, using the trapezoidal rule, let's estimate the area under the curve sine x from 0 to pi. Okay. It's approximately equal to whatever that gives us. Well, we have to pick a value of x, right? Or n. So let's just pick a value like 8, just arbitrarily, right? So if n equals 8, what's that going to give us? What's that fraction going to be? Pi over 16, okay? Times f of 0, what's the sign of 0?
I mean 0.
0.
Sorry.
Okay, so 0 plus, let's do this one. What's f of pi? 0 plus 2 times the sum of f of a plus I delta x. Well, a plus I delta x is just going to be 0 plus I over, so what's delta x? It's just going to be pi over 8. Does that make sense? So pi over 8, everybody agree? Right? delta x is just b minus a over n, right? And then times I. That makes sense? Okay? So then so f of that is just going to be sine of pi I over 8 as I goes from 1 to, no,
Pi.
because we're only double counting the middle ones, right?
Oh, to 8 minus,
So it goes from 1 to 7, doesn't it?
oh.
Right? Okay. See what I'm saying? Okay. So let's do that on our calculator, see what we get. So that's going to give us pi divided by 16 times, and then we're just going to go, where's math? Right there, math. Sum as x goes from 1 to 7 of, because I just skip the 0 plus 0, right? Sine of, oh, you know what, I think I'm in degrees now, so we might have to change that. Sine of pi x divided by 8. Everybody agree?
For the pi over 16 at the beginning, do you have to put it in parentheses to make sure?
You don't have to, because it's going to follow order of operations, but if you could. It might be safer if you're not sure just to do that.
Do we
Yeah.
have to include the 2?
Oh, yeah, I forgot the 2, didn't I? Yep, I have to. Yep. So then.
If you didn't include the 2, couldn't you just multiply with 8?
Okay, this time you could. This time you could, but what if those hadn't been 0? Then, see what I'm saying? Why is it doing that? There. So that works, right? I think. Okay. But it's I have to change this to radians and redo it.
Why do we have degrees if they're arbitrary?
Well, good question. It's just easier to visualize. You know, like if you're thinking about what direction's the wind coming from, it's harder to think about it in terms of, 45 degrees east of south. That makes sense to us, right? I can see why there's some advantage to it. But you gotta be really careful with math and physics with it, because it is arbitrary. And so anytime, like something like this, you couldn't use degrees, right? It's not gonna, could you? On this one problem you could, but if there had been another x mixed in there somewhere, you couldn't, right? If you're ever mixing angular and linear variables, right, then you have to use radians. And so it's just always so much safer to use radians. When you take physics, you get a little bit of more of a, and you do angular physics, which we haven't done a lot of this year, then you get a much better sense of when radians are necessary and when they're not. Okay. So now let's redo that. And there's what we get, 1.97-ish and 1.974, boom, we got it, okay? Make sense? Okay, but you might be asking yourself, what was a little hokey about that?
You arbitrarily picked the number.
I arbitrarily picked 8, didn't I? So how do you know what's good enough? Okay, there must be some way to judge how many trapezoids do I need. There is. Okay, there's a way to do that. There is an error formula associated with trapezoidal rule and with Simpson's rule, but we're not going to do Simpson's rule. Nobody does Simpson's rule. It works, but that's where we would take, instead of a trapezoid, we'd have the top of the trapezoid, instead of being linear, would be a quadratic fit. Okay, we don't need to do that. So for the trapezoidal rule, here's the error estimate that we use. Okay. Okay, what's this mean? So this means that the maximum error that you're going to get based on your choice of n is going to be given to us by this expression. So this part's pretty clear, b minus a cubed over 12n squared, right? But what the heck does that mean? So here's what that means. It means the maximum value of the absolute value of the second derivative of x on your interval, okay? So derivatives are easy to take, integrals are hard. So this still, it's not as bad as it looks. So let's take something like, well, we could do the last problem. Let's say that we want our error. So we have to say, before we're doing this, what kind of error can we accept, right? So let's say that we want, on the last problem, we wanted our error to be, where is the last problem? Oh, right there, right? It's a sine function. Okay, so we wanted to be within 0.01, 1/100th of the exact area, let's say. Okay, so then how could we do that? Well, we could say that our error expression, which is pi minus 0, so pi cubed over 12n squared times this. Okay, we got to figure out what that is, right? Well, f of x equals sine x, right? Everybody agree? So what's f prime?
Cosine x.
What's f double prime? So all we'd have to do then is we've got to find what's the maximum absolute value of the function between 0 and pi, right? So if we took a sine function, and let's just analyze a sine function here, right? Sine function is going to look like if, well, we can do it on the unit circle or as a graph, either way. Let's just do this one as a graph. We always use the unit circle. So sine between 0 and pi, sine would do this, but this is negative sine, right? So negative sine is going to do that, but we're looking for the absolute value of the, does that make sense? And so really the absolute value of sine x, of negative sine x, is just sine x, isn't it? Right? Even if we graph it this way though, it's fine, right? What's going to be the biggest value if we're going from 0 to pi? So that's pi. What's the maximum value that sine could ever have on any interval? 1, right? The absolute value. And from 0 to pi, it does get down to negative 1. So then what is this whole thing going to be for us? Well, 1, right? So that times 1 has to be less than or equal to, what did we say, 0.01, right? So then all we have to do is just solve for n, right? How would we solve for n there? Well, we could multiply both sides by, well, let's do this. We could flip both sides, right? So we'll end up with 12n squared over pi cubed, if I flip it, is greater than or equal to, what's the reciprocal of 1/100th? 100, right? So now all we have to do is just multiply by pi cubed and divide by 12 and square root.
On the very first equation you did at the very top, the general error equation,
Mhm.
why does it say the error is less than?
Okay, so that means that the error, yeah, so why isn't that greater than or equal to? Well, this is the calculation, that's the algorithm that's gonna calculate the maximum possible error for n trapezoids, right? So if we need to be within a tolerance of 0.01, then we need whatever this expression, whatever error this expression is producing needs to be less than or equal to that tolerance. Okay? Does that make sense?
Yes.
Yeah, I can see where the way they write it, sometimes that looks a little confusing. But it's saying, what this really means is the error from the trapezoidal rule has to be less than or equal to whatever number this is giving us.
And then when you
Right.
put the number, you want whatever it is.
Whatever you want it to be, right, okay. So then, if we divide by 12 and multiply by pi cubed and take a square root, aren't we just gonna get n is greater than or equal to the square root of 100 pi cubed over 12, which is what? Square root of 100 times pi cubed divided by 12. Okay, so the answer is 16.07. So what n must we use?
Anything less than that?
No.
Oh, anything greater than that.
So what's
So
so give me an answer then.
17.
17. You get that? So we need, in order to guarantee ourselves that our error is going to be less than or equal to 0.01, we have to have n be at least 16.07, but n is incremental. That's a number, right? It's an index. So we just move up to the next value that's greater than or equal to 16.07, right? So it'd be 17. We could use 20, but in order to get our answer right, we have to have at least 17 of them within our tolerance, right? Does that make sense? Okay, so by the way, that doesn't mean, what if we used 15? Does it mean we're definitely going to be outside of our tolerance? No, it actually doesn't. It just means that for us to be able to mathematically guarantee that we're within our tolerance, we have to pick 17, okay? Does that bother you a little bit, what we just did? Does it offend your sense of mathematical perfection? You know, I mean, isn't that weird? That it does me a little bit. That you can't do this analytically. You can't, it's weird, right? You have to settle on this kind of, this sort of dorky approach where you have to just estimate with trapezoids and then it's not perfect. So how perfect you need it to be. It's a little bit, I don't know, it just offends the mathematician within me that you have to do that, but you do, because some functions are not analytically anti-differentiable, right? You can't always integrate, not integrable. You can't integrate everything and get back an antiderivative, so you're stuck doing this, unfortunately, right? All right, you got it. That's it for chapter 4. I'll put up the assignment. Have at it.
Lunch.